right, continuing with our discussion of tangent lines, slope, and the derivative, we'll look at a figure basically from a geometry type of course where we have a curve, and then the tangent line at this red dot, at this point of the red dot, is illustrated by the red line. And you know, if we move along the curve, you can see that a tangent line would change pretty significantly. So it's defined as a given point. It's a straight line that just touches the curve at that point. Mathematicians would talk about this being the line between an infinitely close pair of points on the curve, where the space between the points approaches zero in the limit. So that's the tangent to a curve. Now here's just an illustration, a video. You can see the source of what happens as we move along the curve as different points. What happens to the slope of that tangent line? You can see that it is at times negative, it's at times positive, and it changes pretty dramatically as we traverse along the path of the curve. Notice too, as this video plays, notice that as we go from a positive to a negative slope, we are at what we refer to as a local minimum or local maximum point in the curve. And notice that the derivative at that point, or the slope at that point, changes from negative to positive or positive to negative. So that would mean that there would be right at the point preceding the change, there's going to be a point where the slope of the line will equal zero. That's one of the ways, given a curve, that we define local max and min, is we take the derivative and find points where the derivative is equal to zero. That'll give us these local max and minima points. All right, so if we let f be some real valued function in an open neighborhood of a real number a, so a is going to be the point where we're actually working. So in classical geometry, the tangent line to the graph f at a was a unique line through a f of a that did not meet the graph of f transversely. In other words, meaning the line did not pass through the graph. It's strictly only a tangent line. The derivative of y with respect to a is the slope of the tangent line at a and f of a. And so what we do is we talk about 2 points because we can define a line with 2 points. So we talk about a point at a, and then f of a obviously would be the y value of that point. And then we talk about a very close point, a plus h, where h is some tiny, tiny number, and f of a plus h. So if we draw a line that connects a f of a to a plus h f of a plus h, that would be a secant line because technically it's 2 different points. So if we wanted to find the slope, we would take delta y over delta x, or delta f of a over delta a, and here's what we would get for that. Now, when you want to define strictly a derivative, what we're going to do is we're going to take the limit of this value as h approaches 0, or h goes to 0. So here's just an illustration of, here's a tangent line, here's a secant line, here's our x and our x plus h, and now what happens in this bottom figure is h is getting smaller and smaller. And please don't be confused by their notation of h prime and h double prime. That does not refer to a derivative. That's just like saying an h1, an h2, and an h3. It's just a notation to indicate that they are moving this point. All right, and you can see, I think this shows a video of that, where we start with a secant line and we're letting h get smaller and smaller until finally in the limit h is almost 0, and then at that point you would have the derivative of the curve. Let's play that one more time. So we're looking for the derivative at the point 1, and finally we get there as h moves closer and closer to our point. Okay, this expression is called Newton's difference quotient. Passing from an approximation to an exact answer, in other words, passing from an m, a slope defined between 2 points on a secant line, to an actual derivative, is accomplished by using a limit. So what this notation means, if it's been a while since you've seen this, is that we're basically going to let h approach 0. Now, if the limit exists, then f is said to be differentiable at a, and f prime of a is a common notation. This is also sometimes written as df dA. A is usually x, so you would often see x substituted for a, and this being f prime of x or df dx. If from this definition, f is increasing if its derivative is positive, and it's decreasing if its derivative is negative. So we can find local extrema, which means local max and min, like I discussed on the previous video while we were watching that derivative line move along the slope of the curve. If we want to find those, we can do that using the derivative. And this is just another example of letting that difference between 2 points approach 0 so that we go from a secant line to a tangent line. All right, well, it turns out that you don't actually, while you could, if you had a given function, you could certainly evaluate that function at x and then x plus some small value h and take the limit of h going to 0, and you could find the derivative of that function by doing that. And in fact, in the beginning calculus class, much time is spent in applying the definition of the derivative formula. However, fortunately for us, once a lot of rules have been initially established, then we no longer have to prove or establish them. So there turn out to be a number of rules. These rules can be found in a number of places. You can Google rules of differentiation. You can look in an appendix of any calculus book. You can look at Wikipedia. You can find them. You can find them in many places. I've just summarized a few here to make it convenient for you if you've forgotten differentiation rules. And one of the most important things that I want to point out, because in engineering, one of the things we concern ourselves with a lot are linear functions. A linear function or a linear operation is an operation where basically the sum of the operation done on the sum is the sum of the operation. So in other words, if I have some function f and some function g, and they're added together, and I take the derivative of the sum, that's going to be the same as the sum of the derivatives. And alpha and beta are constants, and constants are not operated on by the derivative rule. Contrast that to the product of functions f and g. The product of functions, if we take their derivative, it's not the product of the derivative, because basically multiplication is not a linear operation. So what that means is if I have a product of two functions, I have to apply the product rule, which is shown here. If I have a quotient of two functions, I have to apply the quotient rule. If I have a function of a function, I have to apply the chain rule. Here are some additional formulas on differentiation. Here's the limit definition. Right here, there's for polynomials, which are a common function in mathematics, there's a power rule, the product rule, the chain rule, and so on. Differentiation of exponential, it's the one function where you take its derivative, you always get the function back. And there are, like I said, there are tons and tons of tables. Here are all the trig functions and the inverse trig functions. And so you can find derivative formulas for just about any function that is differentiable. So no need to apply that limit rule, but I did think it was important here to talk about it because one of the assignments that we do is a MATLAB program where we take a derivative, basically some data points, and use MATLAB to do that. And so you really do have to understand that derivative rule function.